Well, thank you very much, Andrew. It's really a great pleasure to be here this afternoon with you all. This is the Humanities Forum, and the Humanities Forum is the oldest ongoing speakers program at Stevens. And I'm happy to be here. I happen to know, because back in 1977 when it started, I was a untenured, wet behind the ears, junior assistant professor. Now back in those days, you had to teach not only 3 courses, you, and do publishable work, but you had to have another chore to sort of up the perspective of what was then called the Humanities Department. And the head of the Humanities Department at that point, my late colleague Harold Owen, said, "Oh, we don't have a speakers program. You, Jim, run a speakers program." So I happen to know from 1977 the Humanities Forum has been going. At one point, it had like a real budget. I'm looking at the dean in the back. And we had big parties and big dinners, and had a lot of really high-class people. I won't say anything about today's speaker, but
I can't speak to high-class people, but there is a party that's happening right after this.
I see. Well, that's news to me. What can I say?
So I hope you all attend, everyone.
Okay. Okay. So it's a pleasure to be back here. Now, I had initially intended this to be my swan song. I thought, like, okay, it's like the fat lady singing, got a little avoir du poil here. Anyway, and I was going to, try to convey to you all, a last message, a last song, what I really think was important, the most important thing I would have to convey to you at the end of this career, distinguished or otherwise. It turns out it's not a swan song, it's really an encore. Because me and my young wife have moved already to a continuing care retirement community, which I recommend to everyone here. It beats all other alternatives that I know about. So I'm back, and this is an encore in another sense too, in that I'm going to be repeating a lot of stuff like John here and others have heard ad nauseum from me, but I want to try to hit the nail on the head one more time and beat it into you. So here's what this talk is going to be about. It's what we commonly call oxygen. That's what I want to talk about. And what I want to pull out of this talk is that science is a collection of stories we tell about nature, and that some stories are better than other stories. It's really pretty simple. Right? And this is not me. There's nothing new here in this. I mean, in a large sense, this is a perspective of many relativists and going back to Tom Kuhn and so on and so forth. So in this regard, I'm not saying anything new or making a particular contribution here. If I am making a contribution today, it's with this notion, and that is that all of our stories about nature are dynamic stories. There's nothing fixed out there, and it's constantly changing. It's not simply that we, agree on something within a frame of reference or disciplinary matrix or paradigm or a set of conceptual biases that we have, but that even within those frames of reference, things are changing so much all the time that entities are not stable. Oh, I should say something about this little logo that I created for this talk. I was stoned out of my mind when I put this together, and
it looks like it.
Well, but there's an idea here, and the idea is that we're always looking through. Right? We don't see things as unadulterated. We're looking through, and even when we see things like this oxygen, this big O here, it's out of focus. So that's the idea behind this, and that's really the essence of the talk I'm giving this afternoon. Now, I've given a few Humanities Forums talks in the past, particularly regarding the chemical revolution of the 1770s and the 1780s. I've given this talk, not this one, but this one about the chemical revolution, basically once a decade since the 1980s. And the reason I did it is because I thought people in the chemistry department, our friends in the chemistry department, needed to kind of hear about this and disabuse them of certain attitudes and ideas they have about, well, like what is oxygen, for example. I'm not, the chemical revolution will figure shortly in here, but I'm not making it the main focus. What I want to do today is take a longue durée approach, well before and after the 18th century, to see how different people in different contexts have thought about, again, something like what we call oxygen. And we're just never going to get there, John.
We're already there, Jim.
Wait till we're done. Okay. I owe a word of thanks to Michael Steinman and Greg Morgan for this talk. I'm a historian, right, and I'm not a philosopher. And a lot of what I have to say here are really, philosophical points about knowledge, knowledge making, and the status of claims about knowledge. It's really about epistemology. And Michael and Greg have both been very helpful in giving me, bringing me up to date or up to speed with some of the forefront literature in philosophy of science and epistemology about this. I don't want to push what I want to do in the end here is to make a virtue out of my dilemma, right? If you speak outside of your ken, which in some sense what I'm doing this afternoon, you always have to be very careful, because other professionals aren't going to pay you any attention, as I think several of us in this room, myself included, have learned under other circumstances. But in the end, I want to make again a virtue out of my dilemma and privilege history now over philosophy, in the sense that all of these philosophical claims, all these views about how we know things and so on, have to be set in historical context. I want to make a talk about historical epistemology or historicized epistemology. Oh, okay. But before we do that, I want us all to take a moment, following up on Lindsay Swindle's talk. If you feel comfortable about closing your eyes, I encourage you to do that. We're just going to take a few deep breaths in and out. Okay, so deep breath in, deep breath out, deep breath in, deep breath out, deep breath in, deep breath out. Okay, we could go on for 5 minutes, 10 minutes, or an hour, and that would be very therapeutic, I think. But in the interest of time, I think we can turn the lights back on, or at least maybe this one up here, whichever one is I don't know what it is. Okay.
Yes.
So I don't know if you guys recognize that while we were doing that, what we were actually doing was taking in a special form of energy known as prana. Right? We were this is in the yogic and Hindu traditions, where there's several forms of energy. This is a special form of energy that's out there in the world, and we can take in through our breath, right? But it's not about the lungs. It's not about breathing per se, because we can take prana and direct it anywhere we want to in our bodies. Right? If I've got an ache in my shoulder, for example, I can take prana and put my shoulder, and all the stress and anxiety and stuff released from there. Now, I start here. All right, we got the lights. Yeah. I start here in order to contextualize what we want to think of with regard to oxygen. So, for example, people have had all kinds of ideas about all kinds of things, in all kinds of social and cultural contexts. So here's, I love this image of Homo erectus mastering wildfires. What did Homo erectus, or Homo habilis, or Neanderthalis, or even early Homo sapiens sapiens think about what's going on when they breathe? For obviously, people understood that breathing is important. If you can't breathe, you're going to die. What's going on in combustion, and so on and so forth. Right? So we're going to turn to Aristotle and the Western tradition. But before we get there, I just want to make clear that there are all of these different cultures who've had all of these different thoughts about, generally speaking, what it is to breathe and what it is to have combustion. I mean, what did the people of Stonehenge think about these matters? Or the Egyptians, or the Aztecs, or the people of Easter Island, or any of these others, Incas, Mayans, Chinese, Japanese, Indians, Great Zimbabwe, and so on and so forth. Now, I don't know the answer to any of this, and I'm not aware, actually, whether any anthropologist or any school of anthropology has collected anything like this, right? Before we turn to the West, I think we need to acknowledge that all of these people in different cultural contexts for thousands of years have had ideas about this constellation of things. Okay? And I think we need to juxtapose what I'm about to talk about with the rest of the world in this regard. Okay, now on a little firmer ground, we can start with Aristotle. Now, Aristotle isn't the first guy to begin to think about what the world is made up of. That, of course, goes back to the pre-Socratics. And this notion of there being four elements, earth, air, fire, and water, is actually articulated by Empedocles several generations before Aristotle. But Aristotle, Plato and Aristotle represent the synthesis of ideas about what the world is made up of. Earth, the four elements, earth, air, fire, and water. And in terms of his physics, as all of you know, I'm sure, each of these elements has a natural motion associated with it. Earth and water tend to want to go down to the center of the universe. Air and fire want to go away. I'm not going to pursue that, although that becomes absolutely key for understanding astronomy and cosmology, and this distinction is the root of the scientific revolution and Copernicus's work. I think the key point for us is that fire is separate from air. So heat phenomenon in this view, which reigns until early modern era in the West, the heat phenomena are different from air. Air is not involved in combustion, it's not involved in metabolism, it's not involved in anywhere we find heat, volcanism or any of that sort of stuff. So that's a primary distinction that's going to hold really until we get to Lavoisier, actually. Okay, we might want to ask, well, if you waterboard somebody, as seems to be done occasionally in this neck of the woods these days, you realize pretty quickly that air is important. And so, what was the role of air then for people in antiquity? Now, there is a tradition here, and it culminates in the 2nd century, Roman really, physician and physiologist Galen of Pergamon, who writes all 120 works of Galen around. He establishes the basis of medicine from this time until really Harvey and others. I apologize for this crappy image here. I stole it from that McClellan and Dorn thing. It's like the quality is really pretty poor. But the point is simply that for Galen, there are three separate systems. There's this system with the liver and the veins where you ingest food and it makes blood, and the heart sends that blood to various parts of the body where it's consumed. There's this system having to do with the heart and the lungs, where the function of air really is to cool the heart. Right? The heart is this hot thing pumping away. Well, not pumping. It's whatever it's doing. It's not pumping. It's just like the heart, the lungs, and air form kind of a ventilator for the heart. And then there's this brain and stuff like that. I tried to read for this talk a new translation of Galen on respiration, and it was incomprehensible to me. But I came away for the first time, I never really thought about this before, that people in antiquity really thought differently about themselves than anything we think of today. I mean, anybody from Plato, Aristotle, Caesar, they all have bodies and are walking around with bodies that are just incommensurable with the bodies that we have. Okay. Oh, and air plays a role in making this pneuma stuff, which circulates otherwise. That's the main point. It's all very different. So air is associated with blood, the heart, the sanguine humor, and the season of spring. We might briefly think about Hellenistic alchemy. There's a very important alchemical tradition. And air and fire play a role in traditional, well, I mean, it's Hellenistic. It also exists in the Islamic world, although it's more or less underground, and then really revives with the revival of Europe and contact with these secret traditions. Air and fire are part of it, but really mercury, sulfur, and salt are the key elements in traditional alchemy that are going to be necessary to create the philosopher's stone. I've tried to find out a little bit more about what precisely the role of air is in alchemy. One of my sources tells me that air in this context may function as a basis or vehicle for the Holy Spirit. Right? So in the Christian tradition, you've got God, you've got the Son, and you've got the Holy Spirit. Now, how does the Holy Spirit actually operate? I'm on pretty shaky ground here, but I'm in more ways than one. That it may be that that's sort of the substrate that the Holy Spirit operates out of. Okay, we move to more modern times, and the discovery of the invention of the gas laws, beginning in the 1660s. This is actually a process that takes a couple of hundred years to actually get down really well. This has to do with the relationship between temperature, pressure, and volume of gases. Now, you all know this as Boyle's law. That's just a reflection of your, Anglophilia. It turns out that there's another guy who also did this, a French guy, and we don't, Aiden Marriott. And and part of this, and part of what's important from here on in, is the notion of you've got to have instruments and utensils and machines in order to do this sort of stuff, right? So Boyle is, got a very crude apparatus of pressure and volume mostly, but this sort of works out pressure, volume, PV equals RT, that sort of stuff. And the key for us, I think, is the notion that air, or we'll see this soon in a minute, gases have properties to them. It's not just that this is air stuff there, but it's there are things we can say about it in general, notions about, again, temperature, pressure, and volume. Then we come to the development of pneumatic chemistry in the 1750s through the 1780s. And this represents a real sea change in how people are thinking about these matters. The first is Joseph Black, who discovers fixed air, what we know as carbon dioxide or CO2 in 1754. He pours some, I've tried to figure out what acid it is, I'm not able to do that, but he pours some acid over some chalk, like just English chalk, and it bubbles up and he's able to capture that. And then all of these people with these new gases develop tests in order to see what their qualities are. So this sort of, one of the main tests is the mouse test. You take a volume of this stuff, you slip a little mouse in there, and you watch and you see what happens. Mice don't do too well in atmospheres of fixed air. This stuff is also not combustible, and there are other tests. Henry Cavendish adds to this in 1766 with the discovery of inflammable air. He's pouring acid over zinc, it's bubbling off too. What is it? Well, this stuff, mice don't do too well in it, but boy, does it burn like hell. Quite something. And then we get this. This is Joseph Priestley, in some sense, well, I won't call him the father of modern chemistry. Oh, no, I perhaps should have said something about the transition from alchemy to this kind of chemistry. There's an intermediate stage, chemistry spelled with CHYMISTRY. It's a slightly different stuff. Here we're on, very modern grounds at this point. And Priestley is a remarkable experimenter and is able to produce and then test and determine these various different gases. Nitrous oxide, nitric oxide, carbon monoxide, ammonia, sulfur dioxide, and what he calls dephlogisticated air. Okay. Now this leads us to the heart of the chemical revolution of the 1770s. And again, I'm largely going to skip over this, right? But it pits Joseph Priestley and phlogiston chemistry versus Lavoisier and what we call oxidation reduction chemistry. In essence, and phlogiston chemistry is a perfectly coherent a theoretical scheme. Right? It makes perfect sense. There's a tremendous amount of really hardcore empirical evidence to support it. These people are not nuts by any manner of means. And this notion of phlogiston, also makes, which is part of it, makes an awful lot of sense. This is, you might say, the paradigm of scientific revolutions. And it's not for nothing that Tom Kuhn, in his structure of scientific revolutions, zeroes in on this revolution as characteristic, and classically so, of what's involved in a scientific revolution as we move from one paradigm in Kuhn's terms to another, and there's a process by which that occurs. And this is what I talked about previously in earlier versions, not of this, but when I talked about this. I don't want to talk about it in any detail except for this one instance. Right? And this concerns what contemporaries call mercurus calcinatus per se, right? What we know of as mercuric oxide. It's a very peculiar chemical reaction, and it's only really identified in the 1760s as part of this ongoing revolution in chemistry. And the trick is that you take mercury, everyone knows what mercury is, that nice stuff, cools, liquid. You heat it up in an oven, and it turns into this red powder. That's just what happens. The trick is, you take that red powder, and you heat it up at a higher temperature, it turns back into mercury, and this gas is given off. There are all kinds of things that make this special, notably that you don't need carbon involved as you do in any other kinds of reduction of ores and metals. Okay, so the question is, what is this gas? Everybody get it? You get mercury, you heat it, you get this red powder, you heat it further in an apparatus like this, bubbles off, and the red powder turns back into mercury. The question is, what is this? Okay? All right. Well, here's what a bunch of people said about this in the 1770s. This guy, I forget his first name, Scheele, he's a Swedish chemist, calls it fire air. Now, again, I'm not going to go into the details here, but trust me when I say this makes perfectly good theoretical sense. This is good science right here. The next year, this guy Pierre Bayen calls it fixed air, and he's nuts. Right? He's just, simply wrong because it's not fixed air, because it doesn't meet any of the tests. Early in 1775, Priestley calls it laughing gas, or what he called phlogisticated nitrous air. That same spring, and it's a question about how much Lavoisier knows about what Priestley is doing and so on and so forth. We can leave that aside too. But they both say in the spring of that year that it's common air. And whatever's given off here is just like regular air. It's not one of these special gases, but just regular air, which means it's still regular air. Okay? Later that same fall, Priestley calls it dephlogisticated air. And it's at this point that there are too many chemists in here, so I'm a little embarrassed by having to put it this way. But they say, Priestley discovers oxygen. Priestley does not discover oxygen. Priestley discovers dephlogisticated air. Priestley never subscribes to oxygen. Okay. Lavoisier reads a paper at the Paris Academy in 1775. When he finally gets around to it being come out in print in 1778, he changes it in the page proofs, and it becomes eminently respirable air. And then when he publishes his textbook in 1789, now it becomes oxygen, right? Or what we call oxygen. So, okay, Professor McClellan, you wiseacre. Here we got oxygen. Finally, we got oxygen. Here it is, oxygen. Well, I think it pays to go and look at what Lavoisier actually said. Right? So this is his book, Elementary Treatise on Chemistry, published in 1789, a remarkable year in so many ways. And the publication of this book is key for resolving the scientific or the chemical revolution. But again, that's not important to me. 1789, he calls oxygen, what's he call it? The principle of acidification and caloric. He discovered the principle of acidification and caloric. That's his claim. Right? And at the same time, he coins the term hydrogen, hydrogen, which he calls is the water-making principle and caloric. Now, there's so many ironies here because Lavoisier gets it wrong. Right? What Lavoisier called oxygen, he should have called hydrogen. And what he called hydrogen, he should have called oxygen. Because oxygen is not the principle of acidification. You can have acids without oxygen. Right? Hydrochloric acid, HCl, has no oxygen in it. So, today we talk about, this talk should really be, what is hydrogen? Right? And I suppose we could give the same talk and we're done with the same conclusions. Okay, but, can we really say that Lavoisier discovered oxygen? No, he didn't discover oxygen. Right? Oh, and by the way, these principles also involve caloric. Now, caloric is the material substance of heat. Right? So heat is not a mode of motion here, heat is a material substance. It's not phlogiston, which is a principle of inflammability. This is a material stuff, it gets conserved in reactions and so on and so forth. Right? So that's what, if the clock stops in 1789, that's your best story about oxygen. All right, we're going to move ahead. The next chapter in this tale concerns John Dalton, right? John Dalton's famous English chemist. And Dalton, talk about atoms, of course, goes back to classical antiquity, to be sure. But Dalton is the first guy to come along and posit chemical atoms. They're real atoms. There are no atoms for Lavoisier, right? It's just stuff. Right? Now we've got atoms. And there's some ways in which he's thinking about these things. But so we have atomic, and atoms have no parts. This little hard thing, indivisible, irreducible atoms. Right? You have chemical atoms that enter into chemical combination with caloric. But because hydrogen and oxygen only combine, there's only one known combination of them, certainly at the time, for Dalton, water then becomes HO, H2O. Okay, so in the 1840s and 1850s, there's another iteration of this. By this point in time, caloric is dead, and now we have heat as a mode of motion, surrounded by an electrical atmosphere. So oxygen now is an atom surrounded by an electrical atmosphere, and water is now H2O, by the way. Now, chemistry and electricity, current electricity, right? Something that begins, really as a chemical phenomenon. The battery is a chemical phenomenon. It's the battery, the invention of the battery by Galvani and Volta in the late 1700s, produces current electricity. So in everybody's mind, there's this clear association of electricity in chemistry. And this electrical atmosphere is particular because what is the problem? It's the problem of the chemical bond, right? If you've got these two atoms, hydrogen has no parts, and oxygen that has no parts, what's going to bring them together? Actually, I think I'm going to pause for a second because I'm roasting at this point, and maybe we could open those and get some fresh air in here.
Revenge of caloric.
Is it a good idea? Too much caloric, that's right. Or, we're filling up the phlogiston has filled up the room. We can't breathe anymore, so. Okay. All right, well, this sort of comes to one of the many heads of this story in 1869 with the formal development of the periodic table by Dmitri Mendeleev. Right? Again, atoms are hard, they don't have any parts. In terms of this story this afternoon, I think what's interesting and important is now suddenly when you organize it like this, right, oxygen now has a set of relationships with all the other elements. Now it's true before, chemists knew about certain things combined with other sorts of things, and there were sort of familial resemblances and so on. Mendeleev is not, the first guy to sort of have ideas about this. But suddenly, again, the context and frame of reference has now changed. Oxygen is now understood to be in these particular relationships with these other elements. And again, I think each step along the way here, it changes the story somewhat. Now, in 1897, this fantastic British physicist J.J. Thomson, looking at what he called cathode ray tubes, discovers the electron. Right? This is actually wrong, right? It's not the first subatomic particle, because the electron, as Thomson discovers it, has nothing to do with atoms. Right? Electron's not part of any atoms. The atoms are these still irreducible things, but it's a new particle out there that nobody had ever thought of. If you stop the clock here, you say, what's in the universe? What's in the universe is atoms and a luminiferous ether. Great ether permeates everything, which is the physical substrate of light. Light's not a particle, it's a wave in something, and it's in this ether. So now you've got a world where you've got atoms, you've got an ether, and now we have these little things, which are highly charged. Right? They don't weigh anything, but they carry a big punch. Okay. The next step, and at each step of the way here in my mind, the way we want to see this is, I think, that it changes the context and changes the story. And with Ernst Rutherford, who he'll show up several times in the next few slides, and Frederick Soddy, around 1902, they come up with the theory of atomic disintegration. This is actually what we call radioactivity. And this is another fundamental development, because atoms are not stable things anymore. They can transmute from one thing to another. You start with uranium and you end up with lead. That's a very different view of what atoms are than had ever come before. The story gets a little complicated. William Thomson, Lord Kelvin, is involved in this, and they start to think, that these atoms actually do have parts in the end. And this is Thomson's famous plum pudding model of the atom. It's got positive charges, it's got negative charges, and they're sort of distributed this way inside of an atom. Right? But once we get this far, right, we're a long way from atoms per se. These are not atoms in the way that anybody's ever thought about atoms before. These things have parts, so they're not atoms. Let me come here first, and then we'll go back to Einstein. Ernst Rutherford, a very famous set of experiments, takes gold foil and he shoots alpha particles from radioactive materials through them, and he discovers that these atoms are mostly empty space. Right? Yeah, there's a nugget inside, a kernel deep in there somewhere, but mostly empty space. And so his model of the atom then becomes a hard nucleus with positive charges surrounded by I don't want to use the word atmosphere quite yet, but surrounded by negative charges. Let me go back to Einstein, because here again, Einstein's notion changes everything. That is to say, everything we thought about matter now, atoms, oxygen, whatever, is now actually epiphenomenal, if you will. It's simply frozen energy, as the cliche has it. And this is, in terms of this presentation, this is Einstein's. This is 1905 papers on special relativity. We've now reframed everything in the material world. It's basically energy in a solid form. Okay, we've been through this. Here's another one. Thomson again and his assistant at the Cavendish Labs in Cambridge identify isotopes. Now, I know some of you are thinking that the isotopes are the baseball team in The Simpsons, a TV show, but it's not these isotopes. Right? This is now the chemistry of, in other words, the chemistry of isotopes stay the same. Right? Like so, oxygen shows up in at least 3 different ions, and all it means is that they weigh more. They have different weight. They're not quite the same atom. Right? They have the same chemical properties because the electrons on the outside are doing the same thing as everything else, but still they're still different now. So we can have an atom of oxygen or nitrogen or magnesium or uranium 235, 238, and so on and so forth, with the same chemistry, but it's somehow a different atom. Niels Bohr comes along in 1913, and I want to come back to Bohr later too. But this is his model of the atom. It's got a hard nucleus, and electrons now electrons are subatomic particles circling around in different shells, and each shell can hold so many electrons. Like the first one can hold 2, and so on and so forth. And this very nicely explains the chemical bond, because now hydrogen with 1 electron can be oxygen and hydrogen can share that electron, and therefore going to bond together. All right. Again, Rutherford, it's now identifying hydrogen nuclei as protons. So the kernel, the nub, the nucleus of an atom now is composed of protons, which are actually hydrogen nuclei. Right? So now oxygen and that Mendeleev table now has relationships with hydrogen that it didn't have before. Right? This has got 8 hydrogen things in it. It's kind of hydrogen times 8 with a lot of extra electrons through it. Okay. Now, my goal here is to mess you up. You understand that? Right? So I hope I'm succeeding, at least in the way I want to succeed. Okay, then we have quantum mechanics comes along, right? And that, of course, changes everything again, right? Because now we can't talk about these fixed things anymore. Right? They're not fixed exactly. We don't know where they are. We don't know how fast they're moving. And in essence, we're going to be talking about probabilistic shells, clouds of, where is this oxygen thing? Well, it might be here, it might be over there. A certain probability it's over there, and so on and so forth. Right? We're in the context of theoretical physics in which we have to place these things has now changed unalterably. Okay. I guess we could say finally, because there's always this issue about how much these things weigh and why they don't all weigh the same, and so on and so forth. Chadwick fixes this up with the discovery of neutrons in 1932. So from 1932, in the context of quantum physics, oxygen now has 8 protons, 8 neutrons, and 8 electrons. And I was a chemistry major for a while at Columbia in the 1960s, and this is what I was taught, along with Bohr's shell chemistry. And I still have a very warm heart, a place in my heart for thinking about oxygen and others as being composed of protons, neutrons, and electrons, and a lot of electrons around in various times. Of course, I think that's still what's being taught, but it can't be the whole story. Okay. From the 60s through the 90s comes the experimental identification of quarks. Right? This is now atomic physics, high energy particle physics at CERN and other places. You zap things, you speed them up near the speed of light, you run them into each other, you see what happens. And now they were posited theoretically, and now they're identified actually. Now this is also revolutionary, because what I learned about protons and neutrons as, all right, fine, the atom is not exactly an atom, but protons and neutrons are irreducible still. That no longer holds. Right? Protons and neutrons are no longer fundamental particles. They themselves are composed of quarks of various shades or another. Okay, so let's ask then, well, what is oxygen? This, I think, is my attempt to give you the most up-to-date and current view of what it is. Under the umbrella of quantum chromodynamics, oxygen, atomic oxygen, like this, consists of 8 protons, 8 neutrons, and 8 electrons, which themselves are composed, well, the protons are 2 up quarks, 1 down quark, and 1 gluon-mediated strong force. The neutrons there are 8 of them, 1 up quark, 2 down quarks, and the gluon-mediated strong force. The Higgs boson has now been experimentally identified. A couple of years ago, the theoreticians who posited this won the Nobel Prize. A Higgs boson confers mass on these things, and we're still looking for gravitons, which are going to account for gravity. As I suggested, oxygen exists in 3 different stable isotopes, O16, 17, and 18, and a bunch of unstable ones as well. They capture an extra neutron or 2 or something like that, and they don't last very long. Of course, then there's antimatter oxygen, which is composed of antiprotons, antineutrons, and antielectrons. I'm not sure they exist in the cosmos. They may have existed early, they may exist somewhere else, because obviously, if you put antimatter and matter together, you get like a big explosion. We wouldn't be here if there were a lot of that around. But people have identified positrons. And of course, there's oxygen gas, there's O2, and ozone. Okay. I want us to stop here for just a second. And if I were to ask you before this talk what you thought of as oxygen, I dare say not many of you would be saying anything like this. I mean, Tom would, because John certainly would. And this leads me to this point. Think about this sociologically. I mean, we say, oh, let's go back. This is the best story we have. I think plus or minus, right now it's the best story we have. But who knows this story? Who has access to this story? Who knows anything about this story? And I think the only thing we can say about it is that the knowledge of oxygen, the best knowledge of oxygen that we have, is esoteric knowledge of a priest caste. You have to be trained, you have to be, inculcated, you've got to go through certain initiation rites, and then suddenly, you say, yeah, I know what oxygen is. Okay, well, we're getting towards the end, so hang on with me here. All right, well, what about the future? We've gone this far from, not to mention, Stonehenge, etc., or Aristotle. We've come this far, and again, it's a moving target, right? So, well, what about, what's going to happen to the story, if and when we get something about gravitons, or even more seriously, dark matter and dark energy are the main theoretical issues facing theoretical cosmology, astronomy, and physics these days, and it's a big question, and nobody has any even halfway good answers to it yet. But the phenomenon out there suggests that there's other kinds of matter we haven't even talked about, and other kinds of energy that we don't even really know about. If and when, and I suspect there will be progress in this area, if and when that comes down the pipe, that's also going to change how we think of oxygen. Because it's going to be could have actually practical theoretical effects, right? But it's certainly going to have general intellectual effects about how we think about oxygen. Now I know John thinks string theory has no value whatsoever because it's never going to be experimentally verified or have any evidence for it, and I actually agree with him. So this is something we actually, one of the few things we agree on. There's some others, but we'll leave that aside. But if string theory, these little tiny vibrating strings of 15,000 different, I don't know, if any of that ever, proves out, our oxygen that we just did, back here is going to be a very different kind of entity as well. My views of realism have changed somewhat, although not completely, with the notion that the universe is a computer game imposed on us by some, higher beings or whatever, a big hologram or something of that sort. It's like that Dr. Seuss story, Horton Hears a Who. I don't know if you've ever heard about that. If we're ever able to communicate with the masters of the hologram, that would be something I think would really change everything, including our views of oxygen. On a little less dramatic note, though, what's going to happen to oxygen when the sun expands and becomes a red giant and totally, it's going to engulf the Earth completely and going to eliminate every bit of life if there's still any life. It's going to be several billion years from now, so we can be cool about it. But in terms of this discussion, though, what's going to happen to oxygen when there's nobody or nothing around to think about it? I mean, this is sort of the version of, a tree falls in the forest and all that sort of stuff. But you got to be careful. Well, never mind. If you say a tree falls in the forest, there's still trees, right? Here I'm saying, when the sun obliterates the earth, there's not going to be any trees, there's not going to be any people, there's not going to be nothing, and there's going to be no way to have any kind of reference. So I see, the future of oxygen is the end of oxygen. Now, finally, I want to introduce this notion, which I'm sure is not going to go over well. And that is, does it matter where we use different words? We use oxygen in different languages. Okay, so here's Lavoisier's oxygène, and it's a masculine noun, by the way. Right? So there can't be a feminine oxygen. Right? The French word for table is la table. Excuse me, you can't have le table. There's no le table. Right? And here are the others, all from the Romance languages: oxygeno, oxygio, oxygenio. There's another one in here somewhere. Greek, Japanese sanso, Korean sanso, Chinese yang. I can't pronounce this, but this is Thai. Sour stuff, German. Zur stuff, Dutch. This is Polish, I believe. One of these is Arabic. One of them is Persian. These are the ones I really like. These are the Scandinavian languages. There's 4 different words for oxygen. I forget, since I've made this slide, which is which, but I think oxygen, I think this one's Swedish. Seer, I think, is Norwegian. Ilt is Danish, and Surefni is Icelandic. Now, my argument here, I don't think you're going to like it, but the argument is that if you use these different words, in part because they use different muscles, right? You say oxygène, the French will talk like this. You're talking in a different kind of way. You're using different muscles. It's going to have different impact on your brain and the way you process these things physiologically. So I would suggest, in thinking about oxygen, it makes a difference which length. Oh, I didn't get this one. Kislorod. Good Russian word, and it's actually written funny. So here's the conclusions then of this discursive talk on oxygen. Again, lots of stories about what we call oxygen. I think some stories are better than others. I've expressed my view of oxygen from earlier in the 20th century, and then all of these stories are dynamic stories. None of this is static. At no point is any of this settled and fixed forever. Therefore, the entities in the world are not stable objects. They're moving targets conceptually. So what is oxygen? And here's where I want to use history to help at least contribute to these philosophical discussions, is that it's all in historical context, and the fact that there is no other context. So my apologies to John, who's a naive realist, and to all realists, philosophers of science who may hold a different opinion. So you ask, oxygen, what is it? Well, you tell me. Thank you very much.
We've got plenty of time for questions. So
my nemesis.
Okay.
Naive person.
That was great. That was sort of an archetypal Jim McClellan talk, and it was really great. And you actually pushed back effectively against my view of convergence. But let me just ask the experts: how many chemists are in the room? None back there?
One in front of you.
Oh, you guys are the chemists. My understanding is that there haven't really been any changes in the way that chemistry is taught in, I don't know, 50 or 60 years. I know Linus Pauling said that he completed chemistry when he showed how the chemical bond is mediated by quantum interactions. That was in the 1930s, I think. And so all the stuff from particle physics, quarks, and certainly, you know, the other stuff you mentioned, dark matter and string theory, that has nothing to do with chemistry, really. Chemistry is immune to that. So you're talking about changes at the frontier of physics or sort of ferment and new ideas. Yeah, sure, that's always going to be happening, even if none of it is really experimental science anymore. But in terms of chemistry, chemistry is pretty settled. All the stuff that you describe is people figuring out what is really going on, and they figured it out. This is my view as a complete amateur. I'm just wondering what the chemists think.
We'll let them have their say then.
Yeah. I mean, I know you like Jim and you want to support him.
No, we don't mind you either, right? You're the realist for this. You want to? You're the actual chemist. So
It
you want to try?
has changed, but very little has been changed the way we teach it. That's the bad thing.
Mm-hmm.
And there are loads of things that people like Hugh Packer, they recommended like in 1960s, but they don't get into the curriculum. They don't get into the books. That's the main problem.
But
Higgs-
Higgs boson and quarks, that's
Who cares?
That's not.
They're not in the textbooks.
Yeah, but and who cares? So here, about physics,
Yeah.
for this, we'll still talk about, you know, frictionless surfaces to start with, right? And massless pulleys to start with, and inextensible ropes to start with, right? So these are all approximations. Anyway, these are all models, no matter what. You know, whichever word, whatever, like whatever neurons or something like this. So the question is, how close is the model, and how useful is it for what you're doing? If I have to tell my class about, well, or I'm a biologist actually, I'm sorry about that, but life is important. If I have to bother telling them about, well, before you take your next breath and you do your prana thing, why don't we worry about dark matter or the dark energy that might be passing through or something like that? It's ridiculous. It can't matter, you know, for that. So this model, you know, is, quote, let's say good enough for where it is. We're still going to start with people with, you know, 1 + 1 is 2 or something like that. And there's some, you know, philosophers that have 64 pages of gobbledygook to get to 1 + 1, whatever else, set theory or something like that. But nobody's going to start with that, with something. They're going to start with something that's useful, and then you extend it. And you don't worry about, okay, do I have to worry about, I don't know, let's say the math thing or the physics in math. Do I want to start talking about octonions, you know, for that? No, you know, we'll wait for that some other time when it has to fit. But so I think that the models that we make, and the models that, okay, biologists, we're all making a model right now of, you know, in our brains for what this is, because none of this is real. This is all just, well, I think there's what we call the table here, and you use the word you know, for that. It took 5 years of that nonsense. If you know, so there are models that overlap, and they're good enough. You know, the model that you make. So
if I can interject here, though, I mean,
please.
I think, I think you hit the nail on the head about what's taught in the textbooks,
Right, yeah.
and that's the chemistry I learned. But your notion of chemistry, though, as a discipline, though, you know, doesn't really address these philosophical issues about what's quote unquote really there.
Yeah.
You know, it can have all kinds of utilitarian, practical things, solving problems.
And none of that knows what's really there.
Of course, that's the
It's a
point.
model, but I'm not going to talk to my students
Of course not.
about the dark matter stuff until they figure out how to do stoichiometry.
Even then, you won't talk to them about it.
No,
because
actually
you
I
don't
do,
need to.
because I have a lot of fun doing it.
Well, okay. Yeah,
You know, I like shaking.
You know,
it,
messing with people's heads is a lot of fun.
Absolutely, it always is. But only after they've got a place to stand.
Sure.
Just one more point.
Yeah.
I think your main prediction here, and you are making a prediction, is that there still could be a revolution in the way we understand oxygen and chemistry in general in the future, analogous to what we've had in the past.
No,
And
wait a sec.
that's where I disagree.
Well, I mean, you know, but what I'm trying to fudge in this talk is revolution entirely. Right? I want to go back, to this, that all of the stories are dynamic, regardless of revolution, and regardless of whether they're a framework. So I'm not making a prediction about another chemical revolution, although I think there might be one, given these other possibilities. No, I'm not saying that. So that's not our disagreement. The disagreement is that these entities are fluid and not fixed.
Okay.
If I'm having questions, yeah, go ahead.
So maybe
I thought you came in late. I thanked you for your and Michael's contributions to this talk and helping me at least avoid some gross errors.
well, I've got a nice, easy question for you, maybe. Like at one point you said Lavoisier isn't the discoverer of oxygen. So is there a discoverer of oxygen, or is no one the discoverer?
You are.
Or what's your view?
You just discovered it right now.
Still to be discovered?
That's an interesting question. I don't know if I have a good answer for it. I mean, by the time you get to Dalton, there is atomic chemical atoms of oxygen. So I'd say somewhere between Lavoisier and Dalton, oxygen emerges as a thing in the world.
Oxygen was invented, not discovered, according to you.
I've said it emerges.
I think the stories are dynamic, and I think you're rediscovering it still. So there.
Yeah,
Hasn't
I
been
mean,
discovered
I
yet.
think our
No,
thoughts
I
about
think it's
oxygen
good, too.
as we walk out of this room, I hope, are different than the ones we had when we walked into it. Let's see. Yeah. This is not likely to be a friendly question.
No, it is. By the way, every paradigm has a John Horgan, and I feel privileged to be around our paradigm's John Horgan, the one that says it stops here. It was. So I want to go to my favorite part, which is where the sun expands and destroys everything we've ever worked towards.
Red giant.
So the way that I want to come back to I think a question you posed and implied, or maybe I just didn't catch it properly, is that I think the kind of immediate way that I understood that point was like, what meaningful things can we say about oxygen if we erase our frame of reference, if you're a Kantian, like our a priori structures of understanding? What does all that knowledge we've accumulated leave us to say in the absence of ourselves, basically, right?
Sure.
That's one of the.
That's right. Yeah.
So
Yeah.
I guess I'm curious, like, kind of explicitly, what a historicization of the concept of oxygen helps us with, because that's a question that people argue about forever. And I'm curious, when you add historicization and historicization with the world being destroyed, which is perfect, and I love it. What specific things do we add to that by historicizing the concept?
Well, I think in this case that it comes into being and it's going to go away.
Okay.
That it's not going to exist, after this event. It's going to be, there's not going to be any oxygen.
Well, unless we pop something.
Some grumbling in this corner
Right.
here, but so I think that's the bottom line. It's not like John has this view. It's like asymptotically, we're going to get to a better and better formulation of something that's quote unquote really out there. Right? And I think this view undermines that completely. It's not like we're getting closer to anything. We're just Kuhn's model is really an evolutionary model, right? So we can look back and say, this species emerged from this species and had greater success and so on and so forth. But it says nothing about what's going to happen, right? And I think this little endpoint undermines all of that even. There's no life, there's no oxygen, because there's nobody around to think about it.
What's burning after all the humans die?
You guys are so optimistic about how many
Billion years.
We're just saying, ain't no use.
You tell me.
Who cares? We'll all be around.
Sir.
So what if your talk was not oxygen, what is it, but iron, what is it? Is part of the problem that we can't, or our ancestors couldn't see oxygen, and they knew they were breathing, and there was something, but that led to a different kind of speculation than something that is a little more tangible?
That's a good question, but I think the talk would be the same. I think it could be anything. It just happens that we've got, I won't even say a good record, but at least something of a record that I know something about. Allows me to talk about oxygen in this way. I think iron would be the same thing. Like what are the first people who are smelting this stuff? what are they thinking? Are they invoking gods to do this, and so on and so forth? I still think you end up with the same kind of dynamic, story and moving targets.
Isn't what's important about oxygen is that without it you don't have life? So I think it's important to say that.
Well, I quite agree. I don't want to be
I feel pretty
waterboarded.
addicted myself.
I mean, that's like the whole thread is.
But I think the point is that I got into it a little bit with, the physiology of Galen, but there are going to be different stories about that too. Life isn't going to be fixed. The dean is not happy in the back, though.
So, I'm probably going to sound like a horrible amateur compared to the epistemologist, but some stories, we can tell stories, some stories are better than others, stories are dynamic. I'll buy it. I'll buy it for $1.
Okay.
All right.
I'll take it.
There we go.
That's the funding we get.
Well, I'm gonna get the
What's the framework for validation of what constitutes better? And isn't that kind of defining sort of framework that we call empirical science? That
Yes.
better
Yes.
refers to our ability to tell a story that actually not only describes a phenomenon, but what we're actually talking about, and this is why I like the use of the word model instead of a story.
Okay.
It's a story that predicts the future or
Yep.
allows us to manipulate phenomena, and that's the framework. So, better is something, I guess, that I'd want to throw into kind of a bracket.
Absolutely. No, I completely agree with you, and we're absolutely on the same page. And perhaps I should have said more about what makes something better. It's not just like I like it better or you like it better. It's not that kind of relativity. You're absolutely right. So we want to prefer Lavoisier's oxidation reduction chemistry because it explains the weight gain of the metals in calcination that phlogiston chemistry has a very hard time doing. And we'd say this is a better account for those reasons. So it's actually, I agree with you entirely. It's that these stories make predictions that we can test, and it doesn't mean that we're going to necessarily agree with the results, right? But one account is definitely to be preferred in the long run, and it could be a generation change too. But you're absolutely right. It's not just like, oh, it's better. I like vanilla over chocolate. That's not it at all. And this is an important qualification. So, hi, yeah.
But isn't better in science always add more funding, have more political power?
Who has better data?
There you go. Well,
Look at Soviet biology.
look, I'm already in deep enough hot water this afternoon as it is. When we talk outside, I'm going to agree with you 100%. And I think actually, in the talks I gave about the chemical revolution, what you see in the case of the success of Lavoisier is really a propagandistic, as well as evidence. Okay, I don't want to take away from that because people then had evidence to look at. But he writes his textbook, right, and he changes the language. Right? There's a new chemical nomenclature. So if you're going to do chemistry after Lavoisier, you have to speak a different language. Right? And poor Priestley, goes to his grave remaining a phlogiston chemistry. And so it really is a generational thing. So in all of this, although I do want to give due credit to predictions, tests, experimental verification, evidence, and so on and so forth. There's still a lot of the sociology of knowledge and the social construction of knowledge through these things that don't have anything to do with ideas particularly, but rather funding, who's the boss, and where my career can go, and so on and so forth. The dean's still not happy.
One more question, and then we wrap
I'm
it up.
worried about the priesthood. Not.
Well, you're part of the priesthood, your own priesthood.
Maybe I'm worried about that too. How can we know what oxygen is if there are fewer and fewer of us who actually know anything at all?
Okay.
I'm not so sure the priesthood is getting smaller, even as a percentage.
Really?
I think the knowledge is a lot more available than it would have been in Lavoisier's time. I think it's a percentage of.
Oh, yeah, sure, sure.
So I
Yeah,
think the
but,
priesthood
you know,
has to get
what,
smaller.
you know, what do priests do though? Priests tell us the truth. And what do we do to priests? We say, I believe, I agree.
Or we burn them.
Well, I mean, you know, we can do that, but, you know, the priests are the holders and conveyors of, you know, true knowledge. And our response to the priests is deference. So I defer to you in all matters mathematical.
All right. I'd like to thank Jim again. And as the dean indicated, in the Cal office in Pier 308, there are cheese cubes.
Somebody tell me there was wine, come on.
There might be.
Are there toothpicks that we can build little atomic models?
Absolutely.
We can build our own.
You tell me.